In this video, we are going to implement another matrix-related operation in parallel. The operation we consider is the transpose. So let's see what matrix transpose actually does. The transpose of a matrix is an operator which flips the matrix over its diagonal. That is, it switches the rows and column indices of the matrix by producing another matrix. For example, consider the following 3 by 2 matrix. If we flip this matrix over its diagonal, the resultant one would be 2 by 3 matrix as shown here. The first column of the original matrix had become first row of the transpose matrix and second column of the original matrix become second row. So basically, row and column indices of the elements are going to flip when we transpose it. Okay, now it's your time to perform a matrix transpose operation. Consider the 3 by 4 matrix shown in this diagram. What would be the answer if we transpose this matrix? Please pause the video now and try to figure out the answer. Okay, the answer would be 4 by 3 matrix as shown in this slide. Notice each column in the original matrix had become the row in the transpose matrix. Okay, it's time to implement an algorithm to perform this operation. First, let's implement it in sequential manner and then move on to the parallel version. Let's name our function as transpose and it takes 2 arguments, matrix to transpose and the pointer to matrix which we are going to store the result. And as the first thing, let's check the dimension of these parameters of this function. Remember, after the transpose, number of columns and the rows are flipped. So let's check whether the input matrix row count is equal to the resultant matrix column count and input matrix column count is equal to the resultant matrix row count. If not, we can print an error here. Then I am going to calculate number of elements in the matrix using stored dimensions. Then we are going to iterate for each index in the result matrix and store the corresponding element from the input. So here let me have a for loop which iterates through each index in the results. There are multiple approaches to do this, but I would like to do it from the point of view of the results array index. Let me explain this a bit. We are going to follow 3 simple steps here. First, we get the flipped row and column index correspond to the current result index. Notice here I am taking current ith index of the result array and then find which column and row it is in the result array, and then we can simply interchange those rows and columns values to get corresponding element in the input array. So those are the steps that we are going to follow here. We can get the row from current index of the result array by dividing the index from number of columns in the result array. And we can get the results matrix column correspond to the current index by taking the remainder using same denominator. Then we get the input matrix column and row by exchanging above values. Then all we have to do is to update the ith element in the results matrix using the corresponding element in the input array. So here we can get the index of the input data array by multiplying input row by input column count and then add the input column index in this way. That's about it for sequential transpose implementation. Now I have coded the transpose algorithm in this way because we can easily transfer this into parallel version. For example, look at this for loop. For final element position calculation, the varying numbers like input row, input column are calculated using I or the current index of the loop. All other values are constant after initializing the matrix. So we can simply divide the workload between threads simply by providing different indices ranges to each thread. And that's exactly what we are going to do here. And it is pretty similar to what we have done for parallel multiplication. So let me copy that function here and rename it to the parallel transpose. In transpose case, you need only 2 parameters in argument list, input matrix and output matrix. Then in the process chunk structure, we can first replace the execution logic using sequential transpose logic by copying the sequential implementation. And for process chunk, we need the input matrix, output matrix, start index and the end index for this thread. Now this for loop is going to run start index to end index. The rest of the code is pretty similar to the matrix multiplication case. Here also, first we calculate the optimum thread count and then divide the workload between threads as we did for multiplication. That's all. Okay, let's run and measure the execution time for our sequential version and parallel transpose implementation. So in the main loop, I have simply declared two matrices variable and then perform the time measurements in the similar way that we did for the matrix multiplication case. This is the time measurements I came up with. When element count is 40,000, a sequential implementation is quite faster than the parallel implementation. But when the element count is growing, parallel implementation has outperformed the sequential one. Keep in mind, in transpose, we do not perform any element multiplications, hence the number of operations we perform are much less than the matrix multiplication. That's why sequential implementation outperforms the parallel one when only 40,000 elements are there, but when the element count grows, parallel implementation slowly outperforms the sequential one as the sheer amount of operations are grow.